attending today. We really appreciate everybody's participation. And we have a really awesome presentation for you today. Just know that if you are here for this to count towards your professional development hours, this does count. And we really appreciate you utilizing these technical talks for that. And yeah, so before we actually introduce our guest speaker and go into our presentation for today, I also wanted to share some exciting information about a membership participation activity that we are going to do during this presentation. So for everybody who is participating and everybody who's going to be here towards the end of the presentation, we are going to automatically enter everyone who is present into a drawing for a $15 Amazon gift card. We're going to be giving away 2 of these gift cards. And if you're here on the presentation, you will be automatically entered. And we'll be spinning our prize wheel and see which 2 participants will be taking home an Amazon gift card. And we'll make sure to email those cards to you. So without further ado, I'm going to turn it over to John Todd.
Thanks, Heather. Real quick, I do want to thank again everybody. This is sort of a new approach to our meetings, and so far we've had great interest, and we definitely appreciate you folks being here. Hope you find it as interesting as we do as well. Just want to give you a brief background on Lumashield. Lumashield is a company that they came out of Carnegie Mellon and have been working with the National Energy Technology Laboratory to develop some really interesting and novel approaches to corrosion protection. They're based out of Pittsburgh here, and they are continuing to grow as they are becoming fully commercialized in their novel approach to the sustainable technology for corrosion, especially those using heavy metals and phosphates. So it's a great technology right here out of Pittsburgh, and we're happy to have them join us today to tell us a little bit more about some of their processes and how they're helping prevent corrosion in our world. So without further ado, I'd like to hand it over to our guest speaker, Dr. John Watkins, who is the senior scientist. So John, please take it away. Oh, let me, before I do that, if you guys have any questions, please use the chat feature. You can chat at any time. And then at the end, we'll set aside a few moments to answer the questions. So please use the chat function at the bottom. All right, and without further ado, John, take it away.
Yeah, thanks very much, John. Thanks, John. Thanks, Heather. And thanks to the whole NACE section for sort of, in these difficult times, finding a way to still have interesting presentations going on in a virtual space. And I actually think one of the big upsides to this is that this is a Pittsburgh sectional meeting. If we were doing this in person, our reach is going to be a lot less than it is virtually. So I'm hoping we've got some folks from much further afield than we would usually expect, which is going to make my life a little difficult because I think in Pittsburgh, maybe some of you have heard of Lumashield, maybe you've seen Dave Lubke, the CEO, or myself speak about Lumashield before. We've given several talks here and there over the years, but maybe some of you have never heard of Lumashield. Maybe you're from a little further afield. Maybe you've heard the name. So hopefully I can speak to all of you sort of equally and give you like a background on the company, a background on the technology, talk about some of the exciting things we've been doing over the years, and maybe some opportunities for development, for partnerships. We're always looking for people to work with for our scale up and things like that. So yeah, so certainly reach out to me. My email will be on the last slide and my phone number. And of course, LinkedIn is great. You can always find Lumashield and myself on LinkedIn as well. So yeah, feel free to reach out anytime. So I'm going to be talking through our development of an aluminum oxide alternative to pre-treatments for corrosion resistance and paint adhesion. So if I can find how to change my slide there. Okay, so I'm going to take you through the introduction to what we're calling Lumidize. This is our aluminum oxide coating. How we see that it might be able to replace some conventional pre-treatments, what the benefits of that might be, and how it fits with some specifications we've been looking into, particularly in the military. We've been looking a lot into military applications for this. We've got some funding through the DoD and the Department of Energy. And so we're very, very focused on those military specs. And I think because they're so widely available, they're a good benchmark for us. Then some opportunities where we can contribute to, this is a non-hazardous product, so where we can fit into non-hazardous waste systems, reduce energy consumption, how that might look for lightweighting, and then some other future developments. So first, I just want to start with the origin story. I always like to start right here because this just shows we've grown in Pittsburgh from we were founded in 2014. This is a photo of me on the far left in 2014 working in an actual garage. So we really did start in a garage 6 years ago now. We spun off from Carnegie Mellon University and the U.S. Department of Energy. And now we're up to 7 full-time employees, and we have this new independent lab space, which is right around, if you're familiar with Pittsburgh, it's right out towards the airport in Robinson. And then in 2017, we first introduced our first developmental plating line. This is where we're trying to mimic a plating process from the ground up, so we can start to see how our product might fit into a full-scale process. And then just this year, in February, right before everything shut down and right before we couldn't go anywhere anymore. So very lucky for us, we got our demo done. So this is a commercial demo. We were working with a local company in the oil and gas industry. This is a 100-gallon scale. So this is just very, very recent stuff. And I'm going to go into more details of that demo later. So first, conceptually, what are we talking about? When I talk about this pre-treatment process, so what I'm trying to get across is this is the layer between paint and metal. This isn't a paint replacement. It's the pre-treatment that goes on top of metal to replace something like phosphate that you can then paint on top of, and it's going to give you additional corrosion resistance. It's going to give you a barrier layer. It's going to give you adhesion to that paint. So what we're looking for is really good adhesion into the metal and very good adhesion into the paint. And it's like it's that binder layer in between. So, and yeah, I'll go through some microscope images later, but this is just a really cool one I like to pick out, just because this is how our layer appears on steel at 1,000-time magnification, and it just sort of has this like cracked glass appearance to it that we can grow. So, how does this compare to a traditional pre-treatment? Well, just as a comparison with an industry standard, I call this pre-treatment. This can be a zinc phosphate, iron phosphate. And if you're talking about aluminum now, we're maybe talking about chromates as well. We're talking about that sort of thing. But this traditional like dipped pre-treatment layer, how do we compare to that? Well, we have excellent paint adhesion. It's a drop-in replacement for these things. So it's an immersion technique. It can replace chromates on aluminum, phosphates on steel, and grip blasting. It's a non-VOC process, has no hazardous volatile organics. It's non-toxic. All the rinse waters are non-toxic. The solution itself is non-toxic. It has a visual indicator for when you've applied it correctly. It has a subtle color change to the steel or aluminum, and it's pretty adaptable to pretty much any metal that we've tested so far, and pretty much all paints we've tested so far. We're able to chemically modify this so it can bond to both of those layers really, really well. And the key thing that I'm going to talk about in a lot more detail is when we damage this layer, we get into that steel, we get right down to where corrosion is going to eat under that paint. We can really, really stop that from undercutting the paint and delaminating. So this is now our latest development line, I guess. This is just to sort of outline to you what the overall process looks like from start to finish. So of course, this is reading from right to left. That's just how our line is set up. So on the far right, we have a cleaning step. We often do, we do like we can do an immersion clean or an electro clean, something like that. It's just a support process. Then we're rinsing. Then we go to an acid activation, a very common process for electrode deposited coatings. And then we rinse our acid. And then this tank is the aluminum coating tank. And then post our aluminum coating tank, now we're going into just a double rinse, ambient and warm DI rinse, and that's our process. So it's pretty in keeping with the standard pre-treatment process, but with a bit of a twist of electrochemistry in there. So I'm not sure how familiar the audience are going to be with like an immersion electrochemistry process. This is electrochemically deposited. I'm just going to go quickly through what that means in terms of process, just for people who aren't familiar. So it basically falls into 3 parts. We have a cathode, and this is our part of interest. This is going to get a negative charge It's going to be where the aluminum is depositing. That's the business end. Well, we need to get electrons from somewhere to be able to do our process. So we also need a counter electrode, sometimes called an auxiliary electrode. In this case, it's the anode. It's positively charged. All it's doing is generating electrons. That's all it's going to be doing. And to do that, it splits water. And then the solution itself. And the solution itself is basically water. It's water. It has an aluminum source in there, of course, and some supporting electrolytes. That's very common for electrochemistry, to be able to support charge, so you can maintain a low deposition voltage. So you can see on the picture on the right, these are sort of labeled out in this is in our 5-gallon development line. And I'll go through a little more detail about why is our approach so different. So generally, when you're electrode depositing aluminum, this is a thing you can't really do in the presence of water. And the table on the left sort of illustrates maybe why that is. So every process has an activation voltage where it needs to achieve this voltage in order to be thermodynamically possible. Now, there's also kinetics involved, but I'm not going to go into all the complicated part of that. What it basically means is that at each of these discrete voltage levels, you start to be able to allow a process. And as you can see, water is easier to reduce, that is to generate hydrogen, than is aluminum to reduce and deposit aluminum metal. This is why you can't deposit aluminum metal out of water. But what we realized really quickly is that if we take the premise of, okay, so we can't have water, that means we're going to have to dry everything. That means we can't use standard plating tanks anymore. These can't be open to air. They can't have water as a solvent. This is all getting very expensive. That's a huge expense. And basically nobody's going to want to do that process. And there's some existing electric deposition processes for aluminum, but they do suffer from a pretty niche market because they are such high value processes. So what we're trying to do is come up with something of more of a commodity process. So what we found very quickly was that using this, we have a novel aluminum salt, and what it's able to do is drop this activation voltage down. So now it's able to be in a space where it can compete with water. Of course, we can't deposit aluminum metal because we're still in water and that's going to instantly oxidize. But what we can do is deposit adherent aluminum oxide onto any metal. So that's really the core of the process. So as I said, we got open tanks now. We can use open tanks, as you've seen in all the photos. It's sustainable as well. All that's in this solution is basically some standard electrolytes, our aluminum salt, which is non-hazardous, and water. It's just a water solution. So what this now means is that we can leverage existing electroplating equipment. We can leverage existing processes for cleaning, all the support processes. It's just a drop-in replacement for other types of electroplating. And what that means is it's actually pretty cost effective. We're at scale, we're looking around 7 cents per square foot to coat. So when we compare this to the zinc phosphate, now I choose zinc phosphate because this is heavily used in the automotive industry. I'm going to have a comparison to iron phosphate as well, but also the zirconate-based processes that are sort of pitched to be able to replace these as a sustainable alternative. Well, what we see with zinc phosphate is you need conditioning steps to be able to get this to work. You have sealants, and I'm sure not all of them are chrome 6 based, but some are certainly going to be chrome 6 based, and that's being legislated out of usage very, very quickly. So we're looking to get away from chrome 6 completely. They need lots of DI rinse steps. It's also a very hot process. And largely it can only be done on ferrous metals. Now, there is a caveat to that. There are ways to chemically change the solution to be able to get them to go onto aluminum, but the amount of aluminum you can have in a mixed process is very limited pretty much by the chemistry of the zinc phosphate. So zirconate is kind of the answer to that that's being pitched. But there are downsides to zirconate as well. This is still an immersion process. It works on a lot wider range of metals, of course, but it's a tough to control process from what we're hearing. You need to add like things like fluoride to be able to activate aluminum. That's something we don't have in our solution. And also the corrosion performance is just not as good as zinc phosphate. So we're seeing a lot of benefits here potentially for an alternate to zirconate that can replace the zinc phosphate. So when we compare to iron and zinc phosphate, one of the big differences is in the coating weight. Coating weights for phosphates tend to be pretty high, zinc phosphate especially so. It's a very heavy coating. Our coating is in the range of 500 nanometers. It's very thin, and there's also aluminum oxide. It's very, very lightweight. It also generates absolutely no sludge in the process. This is an electrochemical process, so we don't have a side process that's, say, developing an insoluble sludge that's going to just fall off and accumulate. We don't have that problem. And we can control our process really finely. Now, so electrochemistry does have some downsides, of course. You have to electrify your tank. You have to design certain processes. But with that being done, you have some really, really fine control over your application. If your application is running a little differently, you can just modify some conditions and you can be back to a stable condition of coating without having to chemically modify things. Our operating pH is in the same sort of range as zinc phosphate. We're talking about pH 3 to 3.5, that sort of range. We're also at ambient temperature though, and that's a really big key thing, and that's fantastic. That means we're not having to heat those tanks. It means that we don't have solution loss. There's a lot of upside to not having that sort of heating process, but it is immersion only currently. Now, when we look at the comparison to zirconium-containing processes, now their coating weight is a lot lower. They don't generate so much sludge, but the waste stream can still be an issue. Now, they have to add certain, depending on the alloys, depending on the mixtures, they have to add certain additives to be able to get the process to work. And that can be some phosphate, admittedly less than a zinc phosphate process, but still some. Or they're adding regulated metals like copper, and they have a high fluoride content, things like that. So it's not a 100% sustainable process. Whereas what we're talking now, because we're doing the activation electrochemically, it is entirely sustainable. So now I just want to go into the process control a little more deeply and just talk you through, like, what is the difference between this immersion process and our electrochemical process. So when we look at these chemical processes, I'm using zinc phosphate as an example here, but zirconate works slightly differently, but still it has this driving force of a dissolution of iron from the surface, and that's going to drive iron into your solution. And we know that in a zinc phosphate bath, that becomes an issue eventually. And then by doing that, you're now able to reduce protons, you generate hydrogen, and you get a high pH zone near to your part. And what that does is that drives a precipitation of a zinc phosphate, and that's great. But what we can do with an electrochemical process is we can decouple the dissolution of something like iron from the high pH zone activation area. And we can actually drive this process electrochemically by generating our electrons far away at the anode. And the anode surface, we don't really care what it's doing. As long as it's not destructive and it has plenty of water around to split, it's going to generate plenty of electrons for us. And we can use those electrons to drive this pH to that high level at the cathode surface. This is the steel part we want to coat. And then we can use that. Now, in combination with that, we take our unique aluminum salt, and we can reduce that. And then that oxidizes to aluminum oxide, and we get this very nice adherent aluminum oxide layer that we can build. So that's really the core difference between the two processes, and that decoupling of the electron generation, that's really key for us. And we can then modify this. We can tune the amount of electrons we get with current and with pulse timing. This is a pulse process to really get it to work on some alloys. So we can tune these little dials, and we can make our process go fast, go slow. We can turn it off, we can turn it on. And that's really, really powerful for us. So when I start talking about like changing these process conditions, well, we can generate all kinds of different surfaces. We can generate these different colored surfaces that you can see here. So with different process parameters, we can go from something that looks kind of just about violet colored all the way up to what you might think this might look like. So you think aluminum oxide, you're probably thinking, oh, this is going to be a white coating. It's going to be like an anodized coating. And in some ways, it's kind of similar. But there's a transition state in between the raw steel and this sort of thick, cracked aluminum oxide that's white, where we get this really nice blue coating. And what we found is this blue coating is about 500 to 600 nanometers thick, and it's a perfect paint adhesion surface. So that's what we're really aiming for in all of our current development. And when we start to look at how that works when we start to apply paints, now, I will say we're working with a commercial powder coater, so all the paint data I'm showing here, unless I say otherwise, is a powder coated epoxy resin. Okay, so when we take our coating and we compare it directly to this, in this case, iron phosphate is our standard. This was for a Department of Energy project, so this is the standard we were using is iron phosphate, commonly used. We see after 1,000 hours of exposure to salt spray, there's just tons of scribe delamination away from where we've damaged this paint, and this is a common practice for ASTM tested. I don't want to assume that everyone knows exactly what's going on here, so just let me take a step back. What we do is we put our coating down, we apply the epoxy with this powder coated method, and then we take a knife and we scratch through that paint, make sure we get down into the steel to simulate damage. And then we expose it to this salt environment and we see, is that corrosion getting underneath the paint? And when it does, is it lifting that paint off and causing damage away from the initial scribe site? And in the case of on the left, we see with iron phosphate, we say, yeah, that's significant delamination of this paint at 500 and 1,000 hours. With our coating applied directly to the same epoxy, we're seeing much less, and at 500 hours, absolutely no delamination of this paint. So we're able to protect this paint from delaminating. And that's really what we're looking for here. So as a case study, I'm just going to go back to the demo that we were talking about earlier. So this is a 100-gallon scale demo that we were doing with a partner in the oil and gas industry. And what they wanted is for us to coat the interior of this barrel. And this barrel, we design a process for it. This is a 100-gallon scale. And what they want to do is they want to coat this barrel with something that they can then paint with an epoxy paint that is going to resist exposure to a heavy brine solution close to boiling. And that's some pretty corrosive conditions. So the first thing we did was, okay, let's put our coating down onto these steel test panels. We're going to get and this is now an actual paint. This is a liquid paint being applied. We paint the epoxy liquid paint onto our coating, and we throw that into boiling brine solution for 1,200 hours. And this is the results we see on the right. And again, these are scratched all the way down to the steel. So we see a little bit of corrosion bleed through here, but this paint is not chipping off. It's not delaminating. There is no damage outside of that specific scribe site. So what's really great about that is we're able to protect the paint from delaminating. Now that scribe site, there's going to be corrosion there just because you have bare steel, but we don't see any flaking off. And that's the problem they were seeing, is in the field, they're getting the brine able to attack through the paint gradually. And what happens then is it starts to delaminate all that paint and it's a failure of the entire product. So that's what we're trying to fight against here. And they found chemical pretreatments have been ineffective. Currently, they're using grip blasting. So grip blasting can work pretty well. The problem they saw with grip blasting is that by the time they grip blast the interior surface of this thing, it's starting to pit. And they really have a very, very finite amount of time to be able to apply a paint to this to protect it. So we're looking to solve a lot of problems for these guys. But the core takeaway is our coating is able to resist this really corrosive environment. So then I started to talk about specifications. I mentioned we're going to talk mostly about military specifications just because there's a lot of automotive specs out there. We've worked mostly with military specs. They're very easy to digest. They have a lot of detail in there that's pretty widely applicable. So I'm just going to go through a little bit of this TTC 490 spec. This is it covers all the chemical conversion coatings for military equipment, and that's vehicles, that's all kinds of things. So they refer to this quite a lot, and they have different types specified. So zinc phosphate would be a type 1, that sort of thing. So I'm gonna go through where we fit into this space. So when we look in more detail at TTC 490, aluminum oxide of the type we're talking about here, this will be a type 4 on steel. This is a coating having a greater than 50% organic dry film weight. So we're definitely in the type 4 regime. We're also going to be type 6. Type 6 is specific to conversion on aluminum. That's covered by another military spec, and I'm not going to go into much more detail about that. But what really is powerful is that they also have classes defined. This defines what substrates you can put this coating down onto. So we would be approved for class A, B, and C, which is steel, aluminum, and everything else. We have not found a conductive substrate that we can't put our coating down onto yet. That includes a bunch of aluminum alloys, that includes zinc galvanized steel, that includes nickel plated steel. It'll go down normal to all these. I have a little data to show that a bit later, so I won't go into more detail yet. But then the important thing, they define a form, and the form is how this is applied. So we would be form 4. This is immersion with a rinse step. So that's something that we're dealing with right now, and we're trying to find a way that we can do this without immersion. But I'll talk about that again a little bit later. Now, we haven't tested any of our coatings yet with a military specified epoxy primer. So I would say that as a caveat. But with standard epoxy paints, we are almost certain we can pass the adhesion testing that they require 5B or better with an epoxy primer. We're pretty sure we can pass that. We haven't tested flexibility yet. They have flexibility specs, a water resistance spec for DI water, and a hydrocarbon fluid JP8 immersion test. We haven't tested these yet, but we are pretty confident that we are going to be able to pass these. As far as corrosion resistance goes, we are able to pass this spec, again, not with the military spec epoxy primer, but with a standard epoxy primer, we're able to pass this. But one of the big things is they have a toxic component list where they list several metals and additives that they just do not want in their coatings, and we have none of them. So that's a great thing for us in terms of sustainability. So I'll talk about some opportunities now. The first opportunity, I think, is in automotive. Now, I am not an expert in automotive coating systems and the paint especially, but I'm just going to talk a little bit about how I see that our coating might be able to fit into a standard automotive stack. So a standard stack would have, here's the zinc phosphate. We have a bunch of paint layers on top, one of which is that E-coated primer first. But they also have this activation layer, which has really no thickness. It's just there to improve the adhesion of zinc phosphate. So we can instantly get rid of that activation layer. We don't need that. And we can replace that zinc phosphate directly. And then we see no reason that you couldn't use a standard E-coat process, primer, base coat, clear coat, directly on top of our aluminum oxide coating. So that's sort of what we're going to be talking about, is we could fit right into that coating system. And it would be less hazardous, of course. We don't have the regulatory problems, heavy metals, that sort of thing. So we think we can offer a good amount of value here. So I'll just talk a little more detail about what a standard, like an E-coating line, might look like for an automated process right now. You're going to clean, you have to clean the parts. They get dip cleaned. They get conditioned, as I spoke about. Then they go into the zinc phosphate. This is, of course, a hot process. It's all immersion based, so we can sit right in there, no problem. They're going to rinse this. There's a lot of rinse steps, and then they're going to seal this. And I'm not finding more detail than a lot of these processes are Chrome 6 based. And that makes a lot of sense. Chrome 6 offers a lot of corrosion resistant performance, but it's also very, very toxic, and they're trying to get rid of that desperately. So there probably are some processes that are replacing that, but you do require this sealer step in order to build corrosion resistance for zinc phosphate. And then you've got a series of water rinses, and then you go into your E-coat line. Well, if I now talk about this in terms of how we might be able to fit with our aluminum oxide coating, well, we can eliminate the conditioner step, but we do need an acid activation. We need to make sure that the scale, any oxide buildup on the steel is removed. But we can use a city water rinse straight after this. This is based on our scale-up process that we were doing for our customer. Then we go into the aluminum oxide. Then we can just do a simple double rinse process, and then we're good to go straight into E-coat. We don't need any additional sealing steps. So why might this be interesting, aside from the toxicity and aside from that sort of thing? Well, vehicles are trying to get into lightweighting. That's becoming a big topic. So lightweighting the vehicle frame, lightweighting the coating systems. And what that means is they're trying to put a lot of aluminum, a lot of magnesium alloy into these frames. But right now, zinc phosphate can only deal with a certain amount of aluminum before it starts becoming a little problematic. You can add additive packages to make it better on aluminum, but then these are all optimized for steel. So really, zinc phosphate isn't the process to be doing this multi-material coating. It's being modified, it works kind of, but in order to get to that next level of being able to have more aluminum content without any detrimental effects, without a great sludge buildup, that sort of thing, and at ambient conditions, we need something new. And what that would mean is you can have more aluminum in your car without having all these problems around coating, and that would lead directly to lightweighting. And that's what we're trying to do, is come up with something that can coat all these different materials at the same time. And then it just makes things easier for the coating afterwards. So we can already put the aluminum oxide down onto aluminum. And you might say, like, why would you want to do that? We can already do that. It's called anodizing. Well, anodizing uses the aluminum as an anode. It's a destructive process. It bores down into the aluminum. It doesn't build thickness. But also, of course, you can't anodize steel. So we can put our aluminum oxide coating onto the aluminum. We can also put it onto steel. It's a cathodic process. It goes on both just fine. But it kind of appears like anodized. It's not got the same morphology. Really, the analogy stops at it is aluminum oxide. But there's no chromates involved in our process. And that's something that often comes up in anodizing as well. So we're able to coat this aluminum in such a way that we then have an aluminum oxide that's thicker than the natural oxide, not as thick as anodizing, of course, but it's still paintable. We can still make this a really easy to paint surface. And we've been able to do this on a casting. This is an A380 casted panel on the far right here, and it sort of shows this blue hue to it. We can also do it on 7075. We've also been able to do it in 2024 and 6061. Now the appearance is slightly different across these alloys, but we've confirmed that there is aluminum oxide deposited onto these three, and we're starting to see some good paint performance out of these as well. And that's the really important thing, is how do they perform when you start to paint them. I just wanted to mention as well, I did already say that, like, we can also put this down onto semi-bright nickel and onto electroplated zinc galvanized. This is not quite so useful for lightweighting, of course, but does come up in the automotive industry. These things are used, so we're also able to put down onto those. So like I said, so far we haven't found a conductive substrate we can't put this down onto in some way. It looks a little different based on different alloys, but it works for paint adhesion just the same. So just as a case study, I'm going to go back to this this demo we did. Now, this is not aluminum combined with steel, of course. We have done some testing on some coupons for aluminum and steel where we've shown we can coat both of those at the same time. But our customer had specifically had stainless steel fittings mounted into mild steel, and they wanted all the mild steel coated. They weren't too bothered about the stainless steel, but what they really wanted is this weld joint between the two. They wanted that coated. And that's quite a difficult process to be able to do. I mean, what is this weld joint? What is that alloy now? It's going to be some kind of mix of the two things. So we wanted to make sure we could coat all of the parts of this joint at the same time, with the same process, same time, not multiple steps. And in fact, we were able to do it. So you can see here the picture on the right. We actually masked the end of this stainless steel. So what you're seeing at the end of that fitting is just stainless steel. That's corrosion resistant already. That's good to go. So we mask it down. You can see the mask line. You can see aluminum oxide's applied here. It's not applied at the end. That weld joint, that's got aluminum oxide on it. The mild steel main part also has aluminum oxide on it. So we were able to coat all of these different pieces at the same time with the same process in the same tank. And that's really the power of what we're talking about here. When we talk about multi-material processes, this is the sort of thing we want to do, is no masking generally. I mean, we could not mask this stainless steel and coat the whole thing. They just didn't want us to do that. But we could. So we want to be able to do all this with no masking in one tank. So another opportunity in lightweighting that you may be thinking is, okay, well, the aluminum oxide itself is really light. So already we're beating phosphate there quite easily. But could we modify the aluminum oxide so we don't even need an epoxy primer? Can we go directly to polyurethane instead with the same performance? So that's what we were thinking, is can we just get rid of a paint layer entirely? And this is a direct to metal type system where we have a top coat going directly to the steel with our tie layer in between of aluminum oxide. And in fact, we can. So we're testing this by standard adhesion methods. This is cross-hatch adhesion, and we're coming up with 4 or 5B adhesion directly, polyurethane, this is again powder coated, onto the mild steel with our coating on. When we look at that in terms of corrosion resistance, now things start to get really interesting. So on the left, we have a mild steel. This is an iron phosphate, epoxy primer, polyurethane top coat, both powder coated. Okay, on the right, we have mild steel, our aluminum oxide coating, polyurethane top coat, no epoxy primer. And we expose these to salt spray. 500 hours on the standard system, delamination away from the scribe, it's already failed. At 1500 hours with our system, there's no delamination of the polyurethane, despite the fact there's no epoxy primer. There's absolutely no delamination here at all. So that's really the power here, is we can get rid of a paint layer potentially. That's not going to apply to all conditions, but I think a lot of places are going to see value from that. We can also do it with aluminum. So this is aluminum oxide now, direct powder coated polyurethane on top. Again, adhesion is 5B. And now we benchmark that against something that they might use. So this is a trichrome conversion coating. That's something that's coming out to replace hexavalent chromium. And after 1,000 hours, scribed, they're both the same, our aluminum oxide trichrome. 2,000 hours, we start to see some blister formation around the trichrome sample, not around ours. At 4,000 hours, still no delamination on our sample on the right. Trichrome is still showing these blisters being formed. So we're able to beat that up to 4,000 hours, and I mean that's pretty significant for a direct to metal on aluminum. Now, in transportation, that could mean in some cases, we can start getting rid of the E-coat layer. Can we get rid of E-coat? Can we get rid of the other primer layer? It's basically, we're thinking of different ways that we can generate a coating system that works for automotive, gives the corrosion resistant, but is much lighter weight. And of course, aerospace is even more into lightweighting. They have aluminum frame. Fuel efficiency for aircraft is a huge deal. So is there any way we can lightweight the coating systems on planes? Is there a way we can do that? And that could be a huge thing as well. So we need to do a lot more testing on this DTM. I just wanted to present to you the possibility, what we're looking at, what we're thinking into the future. And then I talked a little bit about, this is an immersion only process. That can be a bit off-putting to some people. In the automotive industry, they're not likely to care very much. That's all immersion anyway. But when we start talking to the military, we hear over and over again, okay, well, I can coat my Humvee. That's pretty doable. We do that by immersion. Okay, great. But what if it gets damaged? And these things get damaged a lot. We need a way that at a depot level, we can strip off the paint, get down to bare steel, we can reapply your product and paint on top of that, and it still works. We need a way to do that. But it's an electrodeposited process. We can't just pour the solution on there. But there is a way to do it, and it's called brush plating. And this is just a one-slide intro to this. This is a very low level of development right now. We just have this proof of concept. I just wanted to introduce you to this as a possibility in case this is a concern for you. So brush plating, pretty much, it has the anode mounted into a sponge. The cathode is still the part. You have electrical contact between the two, and you pump a solution through that sponge to the part, and you're able to deposit. And it works for our system as well. This part at the bottom left, this is a mild steel part that we were able to apply the aluminum oxide coating using a brush system directly to. And that's really it. It protects that surface. We don't have any adhesion data for this yet. This was a Department of Defense project that we were doing a few years ago that really just got to the proof of concept stage. But we can do it, and I think there's a lot of room for development in this space. So just to summarize now, I just want to say the current coating system, phosphate pretreatment, epoxy primer, polyurethane top coat. Also, often this epoxy primer has chromate in it as well. That's a common thing to be able to do. Or you're rinsing the phosphate with a chromate. Chromate sneaks up on you. Just because you're not using a chrome-based process, often these are getting rinsed with chrome just to give that corrosion resistance. So you've got to be a little careful with the current coating systems. They can be pretty toxic. So in the near term, we want a drop-in replacement for phosphate for chromate. So we can just go from metal, epoxy primer, polyurethane top coat. And it would improve performance, it would improve sustainability, it would lower cost, and it would be non-hazardous. And that's the big thing. The long-term goal is, can we develop new coating systems, new direct-to-top coat systems, where we just use our coating, direct to a top coat, lighter weight, still high performance. We need to maintain the performance, of course, and we aim to do that. But we can now coat with less time, less cure times, shorter lines. It's all just going to lead to lower cost, especially if this is all non-hazardous, which our coating is. And that's really where we're looking to go in the future. So now I just want to just introduce the team. So I believe a few of the guys are on the call now listening in. So I hope I did our technology justice. So Dave, our CEO, he's been fantastic. We sort of met at the Department of Energy early on. That's where we spun out from Carnegie Mellon, US Department of Energy. Our operations manager, Blake, our business development lead is Crystal, and she's been fantastic helping us get leads as well. And then we have and Justin is also our business development advisor as well. And then we have a very capable R&D and applications team that are supporting us and have been doing a lot of the work on the ground. So I just want to acknowledge our funding as well, of course. Some of this work was in part funded by the US Department of Energy. We got an award to be able to look at our coatings specifically for amine corrosion in carbon capture systems. That was very exciting work. So some of the work I presented has been based around that. So I just need to give the standard acknowledgement for that. We've also got funding from the Air Force and NSF and people like that. So in a nutshell, I think the single sentence summary of everything I've just spoken about is Lumidize is going to be used wherever the paint touches the metal. That is really our core area. And I just want you to think that anytime you're painting a metal, I think we can add value with our sustainable coating to that system. And again, if you want to contact me, my details are all on the screen. I'll leave that there for the rest of the session. So my email's there, my phone number, find me on LinkedIn, and I'll be happy to discuss with you in more detail. And I hope you got a lot out of this talk. So thanks very much. So I'm just trying to pull up the chat to see if there's any questions. I'm struggling to find it on the screen right now, with my screen being covered in the presentation. Cindy, are you back? Okay. Oh, there it is. Oh. John, are you back?
I'm back now. Yeah,
I'm very sorry. I only noticed you'd been kicked out when I started reading the chat.
Sure, no problem there. The first question we have here is from Emer Flounders. He was asking if you've done any cathodic protection delamination testing, and if so, what did you find?
Cathodic protection delamination. I have to say, I'm not sure what that specific test is. I can sort of guess from what I'm reading, but we have not done that test. So I would love to talk about what we would do to do that, for sure.
Okay. Well, if it's okay, Cindy, would you mind unmuting Emer, and perhaps he could do a follow-up
absolutely
discussion there?
I think I can do it.
Okay.
Yeah.
She's unmuted me.
Hello?
Yes. Basically, I wanted to find out for immersion service, if you have cathodic protection on the item that you're looking at, what is the impact of cathodic protection on surface, especially at a scribe?
Right. So okay. So if I'm right, what you're asking is the coating itself cathodically protecting the steel? Is that right?
Either that, or are you do you have to worry about undercutting due to cathodic protection?
So
hydrogen
the
buildup on the surface can actually undercut the coating.
Right. So okay. So the first part is the aluminum oxide coating itself is not cathodically able to protect the steel. There's not enough aluminum content in there to be able to cathodically do that, like say you would get from a chrome 6 or something like that. But we don't see any undercutting of the paint. I think this is basically due to it's a barrier layer, and it also has very, very high adhesion to the paint itself. And that is protecting it from delaminating. So a lot of the data I showed to do with the salt spray adhesion testing, we don't see delamination of the paint undercutting from that test.
Okay.
Does that answer your question?
Yes, I think it does.
Okay, thank you.
And actually, Emer had a follow-up question as well, asking about the acid etch line or acid etch in the production line. He was asking about where does the grit blast come into play that you mentioned in the case study? And he's more concerned about the profile being such a thin layer and effects of the profile on that layering. Is that correct, Emer?
Yes, that's correct.
Okay. Maybe I didn't. Maybe I didn't explain this quite clearly enough. But it's actually what they're doing currently is a grit blasting just of the mild steel. So they take the mild steel. They actually have a very severe profile on it to be able to anchor the epoxy paint. We're actually looking to replace that. There is no grit blast step with our process. So there is an acid etch, but the acid etch is not of our coating. The acid etch is of the steel to make sure we're removing any oxide that might interfere with the process. So it comes before our electrode deposition.
Right. No, that's fine. I wasn't sure if it was, if you have a surface prep where you have a lot of blasting, and it was such a thin coating, I was concerned about the impact there. But if you're in the intent to eventually go direct to metal, it will eliminate your primer coating, so it's not an issue.
Yeah. None of our coatings go onto grit blasted steel as well. The steel we use is just acid etched. It's not it's not grit blasted steel or anything. And the aluminum we use is also just acid activated as well. We're not doing, say, a process like zincating that you might expect from electrode deposited.
Excellent. Thank you.
Yeah.
Thanks for the questions, Emer. We have another one that just came in from Courtney. She was asking if you've compared the system to any thin film zirconium systems, and if so, how did they compare?
Okay, interesting. We have not directly compared to zirconium systems. So we haven't benchmarked against those. All the benchmarking was done against iron phosphates or against chromate on aluminum. So we haven't compared that directly. So, and also by thin film zirconium, is there something specific that you have in mind? Would be maybe the question. I'm not sure. There's a lot of zirconium systems I'm thinking that I've sort of researched, but I'm not sure specifically.
Okay, that's all for the questions that have come in so far. If there's any other questions, please, feel free to type them in here. We have a couple minutes. I did have a question myself. In part of the process, you talk about, I think there were some sort of salts that you introduce into the water mix. Is there any concern of the creating some sort of corrosion cell underneath the aluminum plating during the process?
So the electrolyte?
Yes. Yeah, exactly. As you're creating that electrolyte, is there any negative impact?
So we were concerned initially about, say, entrapment of electrolyte being like creating a corrosion cell in our coating, which can be porous, it can be cracked. Now, could it harbor some kind of negative effect? And in fact, we've seen that a little bit. If our coating isn't done right, early stages, this was years ago, we did start to see that problem. But we change electrolytes, we find an electrolyte that the electrolyte should, in theory, do nothing. It should just sit there and conduct electricity. That's its job. But of course, it can have detrimental effects. So since then, we've engineered our way out of that, and our coatings are now very, they're mostly non-cracked completely. They're very coherent, and we just really don't see entrainment of electrolyte that causes a problem anymore.
Wonderful. Thank you for this presentation. It looks like everybody, we haven't had any more questions come in. So again, John, thank you very much for your time today and presenting this, all the work you guys have been doing. Very exciting stuff. We're seeing a lot of changes in just coatings and corrosions in general. And it's great to see something that's not only protecting, metal from the effects of corrosion, but also with the environment in mind and also personal safety. So this is great stuff. And we're proud that we're doing it right here in Pittsburgh too. So that's exciting.
Oh, it's great to be in Pittsburgh. I love Pittsburgh.
So without further ado, Cindy, if you could, we do have our little drawing that we promised everybody that we would offer here. Cindy, if you could take it away from here and let us know how we're doing the randomization and the picks.
Okay. John, can you go go ahead and stop sharing your screen and I can go ahead
Yep.
and share mine?
I'm just trying to figure that out myself. Is that done it?
Yes. So let me go ahead and share my screen. Please let me know if you can see this. Can you all see the screen?
We can.
Okay. So we're going to go ahead and do a drawing, and I believe this is a $15 gift card. Is that correct?
That's
John?
correct.
Okay, so it's going to be 2 drawings, and the first winner is Emer. Congratulations. And the next winner is James. Congratulations. And I
Excellent.
believe John will follow up with an email.
Yes, yes. We're trying to find a way to do this digitally so that, trying to replicate what we normally would have in person. So we will
Okay.
work with you as soon as we get off of here. So, well, again, I want to thank everybody, especially John and the Lumidize team for presenting this and taking time out of their busy schedule to do it. I also want to thank everybody who joined us today for taking time out of their busy day. I'm sure one thing that we don't want to do is one more Zoom meeting, but we do appreciate it and we hope you found value in this and look forward to you joining us again in the future. So thanks again, everybody, and have a safe and wonderful Thanksgiving.
Thanks,
Thank
everybody.
you.
Have a good
Thank you.
Thanksgiving. And thanks to you, John.
Thanks again.